In this video, I'm going to relate some progress I've recently made regarding trying to mathematically model Tetryonics. This video is going to make no sense if you aren't familiar with Tetryonics or haven't watched my other video, Tetryonics as explained by Kyle Hill. And some of the ideas I'm going to describe are a bit disconnected because they are separate works in progress that all seem to circle around common ideas. One of the big problems with trying to create a mathematical model of quanta is that finding functions that describe triangles as a surface or cones as a volume over space is difficult. Recently, I stumbled across this very simple function that allows you to define a diamond pattern over the xy plane, which can be modified like so to create effectively a chem-field pattern. And we can further alter it to become 3D such that what we're looking at is a slice of a pattern of cones of alternating polarity throughout 3D space. There's something wrong with this function, however, and that is that you only get this chem-field pattern along the diagonal. We can alter this 3D equation further to make it propagate. So far, this is something we have just arbitrarily defined, which has a triangular geometry, which is useful, but it doesn't describe any kind of actual physics or interactions between separate quanta if we were to try to use it as a model for those quanta. Since quanta are supposed to be self-inductive, I think they have to be described by Maxwell's equations, at least in part. But what is very interesting about this function is that if you treat it as a vector potential and calculate what the resulting electric and magnetic fields are, you can show that the resulting equations for those fields are solutions to Maxwell's equations. However, this triangular potential function does not solve the wave equation in 3 dimensions. It only solves it along the z-axis. This is probably not good. We don't know what form a correct model for quanta will take on, but quanta need to be able to describe waves. So some version of this potential function should be able to solve the wave equation in arbitrary directions. We can modify the triangular potential function such that it creates solutions to Maxwell's equations and itself solves the wave equation in 3 dimensions. But in order to do so, we must change these terms from being a sum to being a product. The result of this is a sacrifice of the triangular geometry of the potential function, and instead of having a grid of cones, we end up with a grid of spheres. A good aspect of the spherical potential function, however, is that it does create a chem-field-like distribution of alternating polarities along rows and columns, as opposed to only along a diagonal line. These are vector plots of the resulting electric and magnetic fields of the spherical potential function. It's a bit hard to understand what is going on. Basically, you have a pattern of rings of curling electric field whose curl points generally along the z-axis, and you have magnetic fields that fountain in and out of these electric field rings. This pattern extends everywhere throughout space as a grid. I am of the opinion that quanta should be radially symmetric, and that if you average them out over a volume over time, they should create a conical distribution as they internally cycle. We can make this into a radially symmetric pattern by reparametrizing the spherical potential function in terms of cylindrical coordinates like so. This reparametrization also creates solutions to Maxwell's equations and the 3D wave equation in cylindrical coordinates. The resulting electric and magnetic fields look like so. Instead of having a grid of electric field circulations and fountaining magnetic fields, we only have an alternating distribution around the origin, but we still have the issue that this potential function is defined throughout all of space, whereas Tetryonic geometries, like chem fields for example, are supposed to be finite in size. Now, if Tetryonics is indeed true, which I think it likely is, then all roads regarding new discoveries in the foundations of physics should eventually lead to it. And there's some interesting work being done in academia lately regarding topological solutions of Maxwell's equations. There's simulations and applications for them that seems very relevant to Tetryonics, and it is a subject that I am delving into next. This is a special potential function that describes toroidal solutions of Maxwell's equations. I found this in a research paper published in the journal Nature. The paper is called Non-Diffracting Supertoroidal Pulses and Optical Kármán Vortex Sheets. The equation is algebraically complicated, but the result is fairly simple and probably relevant to trying to mathematically model Tetryonics. Depending on the values that you put into the potential function for different parameters, mainly these q's and alpha, you get different types of toroidal electromagnetic fields that are self-inductive, in that the toroidal geometry is stable and recreates itself and propagates through space. This is a vector plot of the electric and magnetic fields that is created by the toroidal potential function. You can see that it is basically a spatially limited version of the spherical potential function reparametrized into cylindrical coordinates. And this is a video of different types of toroidal pulses created using the potential function propagating through space, which was created by the same people who authored the research paper. I think this result is so fascinating because it's basically a volumetric version of what I had previously tried to do with leapfrogging rings of point vortices, which had issues with the leapfrogging ring structures remaining stable simply because of it being based upon particles. And it also had the issue where I had no equation that was a known solution for the particles' positions or momentum throughout time, whereas we start with having a known solution of the fields over time with this volumetric technique. This is another video made by the same people that shows what the fields are doing at the different locations in space relative to the toroidal pulse. You can see that it's doing pretty much the same thing as the leapfrogging vortex rings. This is very interesting and I think a promising path to making a mathematical model of Tetryonics because though I have not tested this yet, it may be possible to come up with other topological solutions of Maxwell's equations by combining separate toroidal pulses into configurations from Tetryonics. And this is something that I will investigate in the future. For now, I'm going to finish with sharing one final intriguing observation I have recently made. I've been experimenting with trying to create a macroscopic device that has properties of a chem field, namely the impulse drive. What I've noticed is that for the latest iteration of a mass revolving in a circle with variable speed, after a minimum speed, the position of mass throughout time, if you include the integration of its displacement on top of its position relative to its axis of rotation, it makes a triangular path, where you can envision that if you mirrored and repeated this path by having two revolving masses, you'd end up with something very similar to what the toroidal pulse and the leapfrogging vortices are doing. Furthermore, this motion is characterized by a difference in curvature between the base of this triangular path and the tip. This is interesting because in physics, the most general description of a force is that forces are caused by a gradient in energy density. If you think of shells of equal potential around something like a point charge, there's a constant change of curvature of those shells going out, and it's spherically symmetric, and so you get this divergent force field. Whereas if you somehow made the curvature asymmetric, you'd end up with a force field that points along the direction of that asymmetry. And this is basically what this device is doing. Now this is interesting as an interesting connection to other aspects of my interpretation of Tetryonics. I think the self-inductive nature of quanta should be characterized by rotation around their central axis, and their mass is the second order rate of change with respect to time, the projection of their area into a reference plane. That because forces are created as an overlap between different rotating geometries in the same reference plane, this causes time to only be discretely measurable. Now, if you calculate what this area is over time like so, you get this equation for A of t. And if you do the cumulative integral of this area up to some point in time, you get a function of this general form, t plus sine of t. This function looks like a staircase, and it has a very interesting effect on circular geometries that have been parametrized with respect to angles. If you reparametrize the independent angle variables as this staircase function, it transforms the circles into triangles. So if we transform angles or curvature from changing continuously to changing in discrete jumps, this makes circular things become triangular things. And as we can see with using this reparametrization on the parametric equation of a torus, this works in general. I have not yet found a way to apply this reparametrization to the toroidal pulse potential function or other solutions of Maxwell's equations in general. I don't even know if it's possible. It might not be. But this is a very interesting result because it suggests to me that Tetryonics isn't really any different from normal or accepted physics. What Tetryonics is a very specific reparametrization of all of the existing physical laws and known mathematical equations. The difference between Tetryonics and mainstream physics is in the interpretation of the physical meanings of some paradigm-defining experiments and measurements. Also, though I wouldn't say there is much evidence for it yet, this seems to suggest that if you can use topological solutions of Maxwell's equations to model not just Tetryonic geometries, but their interactions as well, that everything in physics, every phenomenon in the universe is just a result of Maxwell's equations, which I think would be simultaneously amazing and pretty funny. That's all I have for now. Thank you for watching.